Hey guys, everyone. So today is the last lecture. Okay. So just a few reminders. A week from today is your presentations, right? So your term project presentation. So it'll be on Tuesday, and then don't forget we have the final exam the following week. Okay. Right? Any questions about that? Remember, same as the previous exams, closed notes, right? You're allowed your cheat sheet. And it's comprehensive, right? So everything, which it's cryptography, so you need to understand everything anyway. So in this last part of the semester, we've been looking at applications, as you have seen, right? So we looked at SSL and TLS, which is the classic thing. You built HTTPS in a very simple simulation type of a situation. You did, then we used cryptography for defense, like for malware and denial of service attack. And then finally, we are covering Bitcoin and blockchain, right? And this is the last application of cryptography that we're going to look at, right? So I started this discussion, if you remember, on Tuesday. So make sure you go over that. I'll do a quick review today, but we've already programmed the script, right, to create the wallet, if you remember. So we did everything. So basically, we started with creating an identity, the private key, the public key, right? And we used elliptic curves, right? Which is the exciting thing, hopefully, that you've seen how cryptography with elliptic curves works. And it's applied heavily in blockchain and cryptocurrency, right? So that's what we are. And I think we got as far as creating the wallet, which was creating basically a hash value number. I'll review that today, but today we're going to talk about three other important things. So the blockchain, mining. So we're going to talk about how the mining part works, right? So I'll give you a very simple script of that one. Obviously, when you're mining, you're going to be doing this in C++, right? Because that's the whole difficulty of it, right? So that's the whole point. So I'll elaborate on that, but I'll do a simple Python example. You guys want to get into mining, you have to get a powerful hardware. You have to have all the, C code and everything, and installed several things. But we'll talk about the ideas from the point of view of cryptography. In essence, it's hashing, right? Once again, it's basically hashing values. So we'll talk about mining, and then as we do mining in blockchain, what are you mining? You're mining the transactions that take place. All right. So then obviously we're going to talk briefly about transactions and what that entails. So that can be very complex. Okay. Not really the cryptography of it, but just in essence, all the steps that go into it can be very time consuming. So we'll kind of discuss that. And then finally, the last component of it would be a digital signature. All right. So we'll talk about that. Once you've created the transaction, you sign it basically. And this is the same principle that we've discussed before about signatures, digital signatures, except that the signature also happens with elliptic curves, right? So that's the idea. So in essence, that's what we're going to do today. Okay, so yeah, so and this is, as I said, the final topic to round out all the ideas of Bitcoin and blockchain in very simplistic terms, right? So I'm going to go to this bright space here. And then we're going to start the virtual machine and just write a script on mining. So just to give you a simple, to demystify everything. As far as the rest, I'll just go over them. I have the Jupyter notebook. So, right. So this is, we've covered all the topics, right? Malware, DOS. So I'll add a new module here, blockchain. So currency. And basically, I'll just provide the link to where all of this is located. so that you guys can review for the exam. Basically, key takeaways of this, I mean, just understanding, the basic principles of it, and in particular, pay attention to the elliptic curves ideas, okay? So those could be questions on the exam. So here I'll just add a link. So remember, all of this lives on the GitHub, repositories, cryptography, and it's under this folder blockchain, basically. So I provided, so we'll go over this code today. And remember the Jupyter notebook that we did actually in Python on on Thursday is here, this one, right? So I'll add the link to Brightspace. So it's the whole folder itself, and there's more additional reading if you want to keep going. There's a really nice link I added here called an elliptic curve cryptography, a gentle introduction, right? So if you really want to go really deep into that, go ahead. That would be not a fundamentals cryptography, but maybe like advanced cryptography or something like that. A second course in cryptography. So I'm going to just copy this link in here, create a link. I'll say notes and code. And then here is the link. So you have everything that you need for your review. So there it is, notes and code. And then just the final exam, which we will have, in 2 weeks. All right, so now, I wanted to add that link just in case, and you have it now. So now we're going to start the virtual machine. And as I said, the first thing I'll start with is the mining part. Do any of you mine crypto? Have you ever tried mining crypto? You've tried mining? Yeah. So I have known students in the past, actually, that just have the hardware. I had one student that had so many computers in the basement that it would just get really hot in the summer. So think about that, right? So it's an investment of equipment, and it basically is just that processor, it's running and performing hashing operations. If you remember, one aspect that we talked about this semester with regards to cryptography is that performance, right? We've seen how we benchmark RSA, we benchmark AES, etc., just to see, okay, this does take a while to process. Okay. So that's kind of the idea. So I've added this. All right, great. So let's start our virtual machine. So I'm going to go ahead and start the VM. I've given you the link, and I'm sharing the screen and recording. So let's go to the virtual machine. And as I said, I'm just going to do a simple Python script to illustrate the mining process, okay? The idea is just to demystify what it is for us to have an understanding. There's this idea of complexity. So basically what that means is that, essentially you grab some data and you start hashing it. But you have to hash it to a certain level of complexity, if that makes sense, right? Governed by some different kinds of rules. And then at the end of that, you're done and you produce a hash number. And so then basically that requires all those hashing operations to achieve and to arrive at that complexity take a lot of energy and time on your computer. So people are actually spending money just performing calculations. So you might ask, why are they doing this, right? So why do you think they do this? Why would someone get a whole bunch of computers and just run them constant and hash data to get some kind of a integrity thing in the end? Why do they do it? They do it because whenever somebody does and this is the key, right? Whenever someone does a transaction in blockchain, this just is broadcasted into a network. And then all of you, let's say, are miners, you all receive like the data. And you're all like, okay, hmm, let's say that there's 10 transactions that come in. Each one of them offers a fee, like offers a little bit of Bitcoin that you can earn. So because you have limited amount of space in your block, you actually will pick the one that pays you the most. Do you see that? So there's like a transaction fee basically. So then you're like, oh, the seventh one pays the most. You grab that one and you add it to your block. And it's basically the transaction information. This is that ledger thing, right? So you add that, and then once you've added it to your block, then you start taking that whole block and hashing it, hashing it, hashing it, hashing it, and then boom, you've hashed it, and you're an independent person from the people that are doing the transactions. So what you provide is this proof, like the proof of truth or the proof of work, as they call it. And basically that's the in essence, because remember, what is hashing providing? What was the principle of information assurance that hashing provides? Integrity, right? So it's providing integrity. So you're verifying you, and by the way, you don't just verify like hash, you would do other things that I'm not gonna do in this code, like that, but we will see in the transaction, there's gonna be, public keys that are there, the account is there, and then you digitally sign it. So all of that will be done by the miner. The miner will, do all those calculations and verify the digital signature. If everything checks out, then, everything is correct. And then they just start hashing that block, and that's it. That's why it's decentralized, right? So instead of going to a bank and depending on the executives of that bank to validate everything, what do? You independently, as miners, do this proof of work for them and provide the integrity. Does that make sense, guys? So that's the power of, how it works, right? The concept. All right, so let's go ahead. So now, as I said, I'm just going to do a very simple example of mining. We'll talk a little bit about it, and then from there, we'll go back to the Jupyter Notebook and talk about transactions. That's complex, so we're just going to read through it slowly, kind of get some insight into how it works. And it actually, there's a lot of details there that might be very specific to that, because it's the very first version of blockchain, right? So there's no real goal in like understanding every aspect of it, but instead just getting the general idea of how it works, given that Ethereum is going to be different, Solana is going to be different versions of Bitcoin are going to be different if you think about it. So this is going to be a very simplified way of looking at how things work there. All right, so I've given you an overall context, hopefully. So now we're on the virtual machine, so you can follow along. I'm going to go back to our folder. I'm going to create a new script for this one. So let's go to ITS 350. All. Okay. Crypto and blockchain, my folder there. All right. All right, we did the crypto wallet on Thursday, past Thursday. So we did this crypto wallet. And so you have that script. You also have the Jupyter Notebook. Today, I'm just going to create a new script. All right. So I'm going, and then we're going to talk about a few aspects of it. This script, I'm just going to call mining, I guess. Yeah, blockchain mining example. So let's say block banana blockchain mining. Again, this would be very slow. As you know, Python is a amazing language, very powerful. It is much slower than something like C, C++. Rust or those other ones. Okay. So let's go ahead. So obviously, I'm not even going to use PyCrypto, although we could. I'm just going to use a simple library called hashlib import hashlib. And this, the whole point of this is to kind of illustrate that that's all you're doing. You're hashing blocks, okay? And then also we're going to import to have some kind of a timestamp when you're doing these things. You can import time, etc. So let's do that. Okay, so it found the library, so we're all set. All right. Please stop me if you have any questions. This is on the GitHub, by the way, so you can just look it over there. All right, so here, we're going to think about the basic structure of what we would do here. So we're going to have a main function, and then from the main function, we're going to need to have this idea of a block, and think of it as just some data structure. Okay, so that's basically the way that you can think of it. Some data structure. This would be in memory. And think of it as a ledger of transactions, basically. And it's literally, and you'll see, it's like it's supposed to be very short. So that's one nice thing about the whole protocol is that it's supposed to be very small messages, right? But and it contains a lot of the public key, the signature, the hashes, those kinds of things. And then it needs to have some operations, and then basically the values, like how much Bitcoin you're sending from wallet A to wallet B, and so on. All right, so let's kind of think through the logic. So I'll start here with like the main loop. I'm just going to think of this as the main loop section. All right. So this main loop section will need to have some idea of how to mine the blocks. Okay. Let's just say new block equal mine block. So we're going to need to mine a block, right? And basically you're taking some data, hashing it, right? Adding information into it. So we're going to define some functions. So one of the functions is going to be a class. I'm going to do class block. Okay. 1, 2, 3, 4. It's going to have a constructor in it. All right. And then this is going to be some information, such as the data, right? So let's imagine we have some kind of an index. We have whatever the previous hash was. So think of it as the last time that block was hashed, what is the previous hash of it? Previous hash. And then the data, right? And this data we're going to keep simple, but it could be whatever we want. Some control value. Here, let's make it 0 for now. Okay. 1, 2, 3, 4. 1, 2, 3, 4. So this is a constructor, of course, so we're just going to add some identifiers. So an index, some value. So let's just say we assign to an index. The previous hash. Previous hash. And it's going to be previous hash. Then we're going to have the data itself. Data. We're going to want to have a timestamp associated with this. So self dot timestamp. And that's just going to be from time dot time. You see that? So basically, we're just creating the block, and you can see it's nothing more than, it's an object, it's a data structure with values in it, right? And then finally, we're going to have the hash of it. So we're going to say self dot hash, and this one will be equal to self dot calculate hash. Just like that, right? So basically now we're going to define that function. And as you might imagine, that function is just going to take all these parameters, and guess what? It calculates a hash of it. Does that make sense? So that's the basic idea. All right, so let's add that function. Using this class just makes it super easy. So, 1, 2, 3, 4. Right, so we're going to define here the function calculate hash, and you guys already know how to calculate hashes at the self for the class. 1, 2, 3, 4. 1, 2, 3, 4. You guys see that? So now, what do? We're gonna take all the parameters, and we're just gonna hash them. Right. So how do we do that? So basically we can say data to hash. And basically we can just concatenate all the individual pieces of information, right? That, to have this process. Okay. So let's do and I'm going to convert this into a string. As I said, this is a very simplified version of this. This, may be done in bytes, etc. Keep that in mind, that the implementation in C could be a lot more elaborate, right? But this is just to give you an overall idea of the mining process. So let's take this index that we're going to use, self.index. So you can see I'm grabbing, I'm defining a block as being a thing that has what? Some kind of an index, has the previous hash when the last time it was, that block was hashed. The data, so if the data has changed, it has a new transaction, etc. It's in there, a timestamp, right? And all these parameters. So I take all of these now, and I'm going to go ahead and just concatenate them into a single string, for instance, and then hash that. So in this case, I can also take plus. So you can see plus the previous hash. So that would be self dot previous hash plus string self dot timestamp. Okay. Plus the data itself. Okay. Self dot data. Okay. So that should be, and that data, let's convert it to a string just in case. Okay. And then we have that control value, just in case we can have more parameters in here. Self-control, and that also is converted to a string. All right. And basically that's it. So the idea would be that we can hash and hash. So we're going to take something and hash it, and then hash it again, and then hash it again, and keep hashing until some condition is met, right? Which it's going to depend on the different types of algorithms that you're using, but you have some target, right, that you want. And so you keep repeating that process. So that's I guess that's where the mining process comes, the mining term comes from. The fact that you grab a block and then you keep doing something until you achieve something. So it's maybe like digging. All right. But that's sort of the idea. So I have the thing, I have several parameters there, and now I can go ahead and just calculate the hash for this. So what I'm going to do here is just return. All right, and then I'm going to invoke my library hash lib, right? Which is the hash lib, this library over here. So dot SHA-256. We've seen that the SHA-256 is used a lot. We used it actually to create the identities and the address, the wallet address on Tuesday, right? So hashlib SHA-256. Then, if you remember, we actually had the code from scratch, right? You remember, but you can, it's usually better to just use a library. So in this case, now we're going to proceed to to so SHA-256 data to hash. Okay. All right, and then the result of this, let's do hex digest. Hex digest. So that would be the process basically of mining. Okay, so that's the key idea. So we're going to try this. All right, so the function is to create the block and then to run it. So let's just try something. So this takes, so let's go over here. I'm going to skip this for now. Just going to create, I'm going to create a new block, my block. My block is going to be equal to block. And, we're going to use the constructor to define a few parameters just to play with it for now. So it has an index, so I'm going to give it 3. And then it has a previous hash, so I'm just going to say it assumes it's a string. So I'm going to just something like that. Okay. And then it has the data. So I'm just going to say transaction. Data, just something for now, just to test this out. And then some kind of a control, which by default is 0 right now. Okay, so I'm just going to take, I've initialized the constructor. So let's just run it and see if I have any errors. I'm going to do clear here. Python 3. Block object has no attribute control. Oh, yeah. Sorry. I forgot to add that. We have to do self.control. And that's just going to be equal to control. Does that make sense? So basically our little block, and then we're going to try to hash it. Let's try it again. Strings must be encoded before hashing. Okay. So a string, so this is a final string here, object. And so let me do encode. So dot encode like that, right? So let's try it. And there you go. All right, so I just wanted that. So it's the same as like that byte that we used to put in the strings when we were using PyCryptodome, similar idea. So that encode is a string object built-in function. All right, so now, so as you can see, that was pretty straightforward. The problem with that, so you might argue, hey, that's enough, right? But the problem is some people, that now comes in the security aspect and the math, right? Where people say, okay, just one encryption is not enough. It has to have a certain degree of complexity. Do you guys see that? So that's where, more of a iterative process comes in until some condition is met. Okay. So this, I'm just going to give you the overall idea of this as this would start to get complex. Does this make sense, guys? Any questions so far of the mining process? As you can see, it's just hashing basically. And that's so whenever you hear somebody say, oh, I'm, mining, this is basically what they're doing. Sir, do you have a question? Yeah, I'm getting Okay, what's your error? Okay. Mm-hmm. Okay. Have the same issue? I got it. Let me look at yours. See if you can spot it. Okay, open. This comma you can get rid of. Try it again. Okay, go back. Well, I am there. Oh yeah, that's it. I see it now. Int. It should be in it. Do you have the same error in the constructor? Does it say in it or int? Yeah, it's two underscores. That might be the issue. So here, so let me stress over here. So if this is not familiar to you, sorry, yeah. So this is like you guys know from programming, that in object-oriented programming, you have classes, you have constructors. This is the default one for Python, right? And there's two underscores in front, two underscores after the word init. And you use the word self just always to refer back to it though. Does that make sense, guys? Got it? Yeah. All right, perfect. All right. So good. So that hopefully gives you an idea. So if I asked you on the exam, write the code to mine a block in the blockchain, something like this would be kind of what I'm looking for. So obviously the key thing is this, right? Grabbing the parameters in there and understanding that you are in fact hashing them. All right, so let's think about this. All right, so now let's think. So this is, I'm going to give you some intuition, right? Blockchain. What is that? Who can just, how would you define blockchain? How would you define blockchain? Chain of blocks. Blockchain, chain of blocks, right? Huh? Well, well, think about it. Blockchain, chain of blocks, right? So how do we kind of think of this idea? Do you want, what do you want in a ledger like this? You want the transactions to all remain. Do you see that? You see that idea? You want everything to be there. It was like this, then it became like this, then it became like this. Then you see what I'm saying? So let's think about that idea by simply creating a list in Python. All right. We're going to have what is called the Genesis block. And you may have heard of that term, and it may sound complex, but actually, just think of it as the first element in a list called the blockchain. Do you see what I'm saying? So let's think about this idea. Okay, so I'm going to go over here. So this was just an example, just to test that my block tool actually works. But let's go ahead now and get into this. So I'm going to create the blockchain, right? So remember that I've said, and hopefully, what is the blockchain itself? I think of it as the set of wallet IDs, addresses that were derived from a specific elliptic curve. Do you guys remember that? We talked about that on Thursday, where we had, remember that everything comes from the world of this elliptic curve that we have, which we have extensively discussed. And then we know that we have points and we calculate other points and so on. All the values that we use are dependent on that graph. So that's kind of like the universe of our blockchain, right? But then, of course, we also have this construct of the blockchain with numbers derived from that, because all this data contains what? All this data contains transactions, and the transactions contain the public key, not private key, but the public key, right? And things, signatures, and so on, which are all coming from that curve, right? But now we can think of as having this construct of the blockchain. So if you look at what I'm going to do here, I'm going to start my blockchain as a list, and that's basically a list in Python, as you can see. And I'm just going to have a function called create the Genesis block. You know, Genesis means like the beginning or something like that. All right, so there you go. So I'm going to define this Genesis block, and basically, actually, what I'm going to want to do is just print it out. So I'm going to do just to view it, I'm going to print out my blockchain, or my chain of blocks. Currently, my chain of blocks has one block. Which block? The Genesis block. Okay. So now I'm going to say over here, print blockchain. For instance, blockchain. Like that. Make sense? All right. So the first thing for this to run, we also need to define this. We also need to define this function called create Genesis block. So I'm going to do def create Genesis block, right? Just like that. So this is not a class, it's just a simple function. And what does this function do? It basically returns the Genesis block. So I'm going to do 1, 2, 3, 4, return. And so we instantiate the first block. You see that? And so the first block is going to have an index basically of what? 0, right? And so that gets converted into a string. And then we have, what's the next parameter? The previous hash. So what's the previous hash here? It's the Genesis block. So you might argue it's maybe a 0 or something else. Okay. And then finally, something, I don't know what the actual Genesis block has in it for Bitcoin. I assume whatever. So I'm just going to say here Genesis. Remember, at the end of the day, it doesn't matter because it's all hash, right? So Genesis, but let's say Genesis block, something. Do you see that? So now this instantiates the very first block of my blockchain. So I'm going to do Control X, Y. And there it is. There, as you can see, is the blockchain. Okay, with our first block in the sequence. Okay. So now what are we going to do? So what do? Let's consider, let's see here, previous hash. Okay, so now we are going to, I guess, the first thing we can do is create a new block. How about that? So let's create a new block in the blockchain, right? So let's do that. So let's go back to the code, right? Got our Genesis block. So we're going to need to have some code here. All right. So let's just say blockchain, and then a list you can just index. So we're going to grab that block, which is index 0, and let's assign it kind of to this variable previous block. Like that, right? So we have a variable previous block, and now we're going to iterate. So let's do for I in range, and we're going to specify a range here. So let's just try from 1 to 4. Okay, so we're just going to iterate and kind of see how we could create some blocks. All right, so 1, 2, 3, 4. So now what do? We are going to need a function called mine block. Okay. So we're going to define that. We're going to create new block, and we're going to assign to it the result from mine block, right? So we're going to mine a block. Oops. So we need to define this function, and we'll do that in a second. And this function would take the previous block, okay? And then it's gonna, so this is a different function from the block function. This can take some information. So I'm just gonna say here some data. Okay. We're also going to have in here some information about the block itself. So let's try this like that. This is the formatting. Oops. Formatting. So I'm just going to add in here block format string I data. Just some information, okay? So we're keeping it simple. And then we can think about where the transactions would go and so on. All right, so, and then this one looks here. Why is that? Oh, yeah, the 2, right? Yes, thank you. There we go. All right, so let's just add this Sunday. Right. So all I'm doing is we have our blockchain. We're thinking of it as a list of different blocks in the chain. And now we're just going to try to create new blocks, right? By having an operation called mining of blocks. So this should return another block. And then what do we do with that new block? We add it to the list of blocks or the chain of blocks. All right, so let's do that. So our chain of blocks is called blockchain, which is a list. So I'm going to do block chain. Just like that. All right. Oh, sorry. This is a list. So dot append. And we're going to append to this the new block. Just like that. Okay. And then now previous block becomes what? New block. Right. So we're going to. The previous block is no longer the Genesis block, but it's just going to be the previous one. Previous block equals new block. All right. And finally, we can say something like, block I mined and the hash value of it. Remember that at the end of the day, we're just creating all these hashes for all as we're, doing the process of mining, right? So I'm going to do here, and the whole thing is proof of work, right? So you have the data in the ledger, and you also have the hashes that you're computing. Okay, so let's print here, and again, I'm just going to use that format string block. This should be I, some kind of an index, mined. And then we're going to say here another format string, new block. Oops, new underscore block dot hash. So the hash value that we computed. Okay. So this is just so that we can see what's going on. We'll print those values, and basically we're showing evidence of mining, etc. All right. All right. So that should be correct. We just, at this point, all we need to do is define the mine block function. Okay. Any questions so far, guys? Is it making sense? Yeah. All right, great. So this won't work because we haven't defined this function. So that's the next thing we need to do. So let's add it here. All right, so let's go over here. All right. Yep. So define mine block. That's the name of it. Yeah, mine block, which takes previous block and just some data, right? So the index and some things in there. So mine block. Colon. All right. All right, so I'm going to say previous block, comma, and then I'm just going to say data 1, data 2, data 1, data 2, just like that. One, two, three, four. Right, so now what do? We are going to proceed to create this new block, or a new block in here. So let's do new block, which is block. Or we're going to use our class new block just like before, okay? Or block, sorry. So this one over here. Make sense? And we're just going to use, so if you notice, when we created this block, it had some kind of an index. It has something called previous hash, right? So previous hash referring to the previous block and its corresponding hash. It has some data, right? The timestamp, some kind of a control, and then we have the function to calculate the hash for that current one. So that's basically it. So you can see there's like a chain where the hash of one is used in the next one, and then the hash of that one is used in the next one, and so on. And this is how you start mining this blockchain from some genesis block to some ending block. And you can see how all that hashing can take a very long time and supposed to provide better security, as you can see. Questions? Yeah, so it's a simple example, but I think a good one. So let's go ahead then and try to finish this up. We're almost done. So we're gonna need we had an index. Did previous block have an index? The genesis block. Yeah. So the genesis block had an index of 0, right? So it had an index. So then this is going to be +1. So let's do that. Okay, well, that should work. So it should be previous block dot index, which was 0, +1. Previous underscore block dot index +1. It's a increment thing, basically like a counter. All right, then after that, what else do we need? We need to define a hash. That would be the next field, previous hash, and then data, basically. Okay, so the previous hash will be depends on the genesis block. So I think the previous hash for the genesis block, I just code it as 0 if you see that, right? So I'm just gonna add that in there. But once we get to the second and the third block, obviously those are going to be actual proper hashes. All right. So let's take a look at this one. So previous block dot hash. See that? So we just add the hash of it. And then of course we're bringing in our data here. So that would be data 1, data 2. So let me just add total data, and we can say data 1 plus data 2. That's fine. So we concatenate the data in some way. This would be more like a programming thing, not so much a crypto. Oh, this should be true. All right, and so we can add total data in here. Right, and if we look at our block, that's what it took, basically. And the other parameters are provided. So once we have that, we can calculate the hash, basically. So we can say new block dot hash, which is this one, right? So that's going to be right. I guess this is just a default. Yeah, I get it now. Sorry. Had a little So basically, it by default calculates that hash, but then we can replace that hash if we run the function again. All right, so here I'm gonna do new block hash, and basically new block dot calculate underscore hash. You see that? Just like that. And that's it. So basically, we create all the parameters. We're going to use the information from the previous block, specifically the hash value. We don't even care for what's in there, right? But just the actual hash value, and that should be it. So return new block. So if I did everything correctly, this should work, and we can basically start creating our blockchain of events and this idea of mining the blocks. Now, here, the last thing that might be missing here is that I may need to have some kind of if statement here, if complexity met. Do you see what I'm saying? So I need to have some kind of an element of measuring complexity, right? So that has to do with the type of hash number that I've been able to calculate, et cetera, or the number of hashes that I perform, one of those general ideas. But let's just keep this like this for now. So I'm going to go ahead and test this out. So this should run, I think, unless I have an error. Yeah, there you go. So I blocked, I mined, right, the block from the Genesis block. I did my mining, and you can see basically that I created this blockchain of hashes. Do you guys see that? Does this make sense? Yeah, please go ahead. Yeah. Mm-hmm. Let's see. Which function? In the function mine block? Oh, the four at the bottom? Yeah. Where? Here, this one here? Yeah, so F is a format string. So what that, you remember how when we did PyCryptoDome, we would put a B in front of the string or something? This is similar, right? So I'm putting in this to format it basically. So it means that I have a string, and then whatever I put in curly brackets is a variable that I'm going to insert in there. So in that case, the variable is this I over here. So the value of it should go in there. Does that make sense? It's just a Python thing. All right, let's take a look at the blockchain too, because I'm creating this blockchain, right? So blockchain, just like that. That's a list of blocks. So let's run it. And there you can see my blockchain consists of the actual blocks. 1, 2, 3, 4. These things might be the thing that, this is what gets loaded into Coinbase or one of those websites that show you information, right? Show you the transactions, the ledgers, etc. But the key thing is this process of having these values, which someone can't go here and change it and say, no, I received 30 Bitcoin instead of 20 Bitcoin. Why? Because if they change this one, the hashes wouldn't work out. Do you see that? So that's the whole integrity aspect of blockchain, which it provides. All right. So that's, in essence, the idea. As I said, I'm just going to add the part of some complexity, and that's just really, math and stuff. So I'm going to keep it very simple, but I'm just going to do. So in the mining operation here, you would need to verify that you've achieved a certain degree of complexity, right? So it's not just in the blocks, but for every block, you're going to repeat the process until you have achieved a certain level of complexity. So you would do something, for instance, like a while loop. So you would do, let's say, while, you know, let's say that there's going to be a difficulty value. Oh, I'm kind of just keeping this very generic, but difficulty. So let's do this. So, uh, yeah, so let me actually show you something. All right. So I'm going to go down here. I'm just going to show you what this operation does before I implement it because it may not be obvious. So let's do a print statement. And I'm going to say 0, right, times difficulty. And let's say the difficulty is equal to 2. You see that? So it's just a variable, an integer in there, and then I'm doing this operation, so let's print it out. So as you can see, it just repeated that 0 twice, right? So let me do like 5. Or actually, let's do 7. You see it has 7 zeros? Do you guys see that? Make sense? All right, so this is like, imagine, right, that a hash value that starts with 5 zeros is a pretty complex hash value to get. Do you see what I'm saying? Then this is kind of a way that you can say, okay, it's more secure when you've calculated a hash value that has 5 zeros in front of it. It's going to take quite a bit. Do you see that? And so this is a way of providing security with the integrity of the blockchain, but also to achieve a value that meets that condition requires a lot of hashing, which means your hardware, right, is going to spend a lot of time doing this, crunching the numbers, if you will, consuming a lot of energy and so on. So that's why not everyone has a miner, right? A computer that does crypto mining. Does that make sense, guys? So this is an idea to illustrate why they pay you money to do this, because people imagine if everyone was mining with these supercomputers, right? It'd be consuming a lot of energy and so on and so on. All right, so let's try it out now. So I've created that example just to illustrate what it does. Let's start with just 2. So this I don't need anymore. So I'm going to comment it out. So now let's go back here, right? So if you can see, I'm doing the mining. I'm going to set a parameter of 2, and this could be, defined anywhere else. So it doesn't, but I'm just for convenience putting it here. And then now the mining itself will not stop until I have achieved something. So for instance, while not new block dot hash dot starts with, and then the thing that I just did. So 0 times difficult. Do you guys understand? So basically, I define this as being a way of measuring that this is a pretty complex hash. It has to meet this criteria. In this case, I want it to have 2 zeros and start with them. Okay, so let's go ahead. So now you would do this in the while loop. 1, 2, 3, just like that. Make sense? All right, so let's try this one. Clear. Oh, colon. Thank you. Here. There we go. Thank you. Let's try it. Do you see that? It just printed the Genesis block, right? What's it doing? Mining. Crunching the numbers, as you will. Huh? It's taking its time, right? But what is that ensuring? It's ensuring that you're doing a ton of hashing. Do you see that? So that's in essence the mining operation. Okay. You can have a variable called nonce, and what the nonce is basically like a counter of how many times it took to hash a number. Do you see what I'm saying? So that's the last, because then you can use that as a metric also of what the complexity. But you can see here, right? So Python's not great for this. You need C, C++, and then you'd need a powerful computer and so on, specifically designed for these kinds of things. But anyway, so the last little bit that I want to add is I want to add this nonce, this variable basically that will give me some information on the number of times that it took to create these hashes, just so I have some piece of information. Okay, so I'm gonna add the nonce to the block itself, and it's a metric of complexity. If you look, it's still, if you have your laptops or something, feel them, like, feel is that yours? Is it? Yeah. So there you go. So you can see the processor is going, it's heating up. We have some students whose computers are starting to catch on fire. And so it gives you an idea of the whole mining process, basically. I would suggest you kill it. I only did 2 zeros, by the way. Imagine if you take that complexity a step higher, right? So it's a tough one. So let's just add the nonce back. So I have index, previous hash, data, timestamp, control. So I'll add this, whoops. Nonce, and nonce initially can be 0. It's just a counter. So basically something like this. So self dot nonce. And I'm going to just increment it to 0, right? So what I'm going to do as I'm in that while loop, I'm just going to be incrementing that, and then it gives me some sense of what happened. So over here also, I'm going to change the difficulty to 1, okay? So I'm just going to change the difficulty to 1. And then now in here, I'm just going to do new block dot nonce equal new block dot nonce plus 1. All right, so just to increment this, so let's see what happens with difficulty of just 1. Okay, still takes a while, right? So anyway, that's basically it. So let's go over a few notes, and then let's leave it for a second, see if it finishes out. I just want to see like how many in the while loop it has to do to calculate these hashes of a specific complexity. So it basically gives you an intuition of the number of repetitions. But in essence, we went over. So let me go to the. I'm going to switch over. I'm going to switch back to Brightspace. And I'm going to switch back to the repo where everything is located. So essentially, we went over the block function, right? So we went over the block function. We figured out how to calculate a hash. Then we looked at the mining process. We have a difficulty parameter. We calculate the block from the previous block, which has the data basically that we're passing to it, the transaction. And then we do this loop, right? Repeating it. And then finally, it produces a block. We also define the function for the genesis block. We define the blockchain, which is just, we think of it as a list of a chain of blocks that we can index out actually from the list just by this number. And then basically we define for I in range, calculate, different blocks basically. So here, obviously, I could have added more information about, new transactions, things like that, but I don't have, I'm just having the generic data variable, right? You can build around it. Remember that, as I've said, Bitcoin and all of that is basically a startup, a company, and they're constantly developing code around these things to provide more services. All right, but anyway, so we create we mine the block basically, which is giving it the previous block some data, doing the processing, getting a new block, adding it to the blockchain, and that's basically it. Any questions, guys, on this one? Did it finish for any of you? No, still going? Yeah, so mine is probably still going. Yeah, still going, unfortunately. But yeah, so that concludes this blockchain mining exercise, basically. Okay. All right, so I'm gonna have to kill it. I'll you guys can play with this at home and see how long it takes. It's not a homework or anything. So I will load this script on the GitHub. I'm gonna reset this difficulty to 0. All right, let's try it now. And you can see here, it does do it, block 1, 2, 3. We can grab one of the blocks to see if the nonce change. So I'm going to do, but it probably didn't. So, but just to show you like how you could have looked at the nonce of one of these, let's grab. So we print the blockchain itself, then you can print, let's say the last one. So it had, let's say 2. So blockchain 2, right? So I'm grabbing that block from the chain and I'm just asking for its nonce, which I would imagine it's probably 0 in this case. Zero, yeah, 0. There it is. Make sense? Obviously, if you set that difficulty to 1 or 2, that number is going to change and it's going to reflect the number of times that you have to like crunch the numbers to get that block. Any questions? All right, so that concludes the exercise of mining blockchain. The last thing that I want to cover is transactions. All right, so basically you have an account, right, and you're going to transfer some funds from one wallet account to another wallet account, some Bitcoin, right? So that's pretty extensive, so I don't want to spend too much time on that. It's honestly, just read it, all right? That's what I would say, read it, because there's a lot of details. I'm just going to highlight in a very brief way how that works, okay? And also because it's too specific to the protocol and things like that. All right, so I'll go over this idea. So let's go back to our Jupyter notebook from Tuesday. So I'm going to go over here. So if you remember, on Tuesday, we went to the repo and I added this. Oh, yeah, no, that's fine. And I added this. All right, so I've already covered how to calculate the wallet and everything. Just a very quick summary, because this might be a question I do ask you on the exam. You know, how do you create a blockchain wallet or a crypto wallet? So how would you summarize it? You have a password, 10 words, right? If you remember. So first of all, there's the curve, right? So that's the elliptic curve. It looks something like that. And you can check if a point belongs to the curve or doesn't belong to the curve, right? Remember that when you have a point in the curve and you add or multiply, right, you have a special operation, okay? So basically we have a starting point. We can check if the point is on the curve. So this is just review from Thursday, right? So we saw that true, okay? Then we take something like a set of passwords, maybe 20 passwords, and we basically just from that generate a number, right? So and this is sometimes called the private key. So you'll see this private public idea is simply a random integer that should meet this condition, right? So okay, so you have this value that is calculated from the password called a secret key. And then that secret key is a number, this integer, that you're going to use to calculate your public key. So the way that you calculate that is basically by doing this operation. So for instance, you calculated 2, and then you have a point G, right, which was X and Y. So if you say that integer was 2, then it's G plus G, or 2 times G, basically. If you had calculated that number to be 3, then it's G plus G plus G, right? So this is all from the previous lecture. So you guys can double check on that. So if you notice, these operations like this multiplication here, it's not a normal multiplication, right? Remember that. This is it only happens in the geometric curve. And basically you define that operation in this function here. And then what you do is you do that, right? So the point, basically here, think of it this way. You have a point, G, and you're saying whenever you use the asterisk, you can reference that as being this thing here, R mul. So that's the asterisk. So you're saying, okay, whenever I have this point and I use the asterisk on it, which is a multiplication type of thing, right? I'm going to invoke this function, which is defined over here. Okay, so that's why when you guys do 2G, 2 times G, right? What you're doing is actually the geometric interpretation of that in the geometric curve, okay? But this times is basically this, which is defined by that, which is this function over here, okay? That's the geometric operation of it. Does that make sense, guys? Any questions on that? This is a tough concept to understand if you haven't seen this before in Python. Okay? So we're literally like changing the meaning of a symbol, if you will. All right, so anyway, once we've calculated, so we calculate from the password the secret key, which is a number, and then we multiply it times the G, which is a point that everybody knows in the curve, and that is your public key. So effectively, this is like your private key, and this is like your public key, okay? All right. And remember that the public key is actually X and Y because it's also a point, okay? It's also a point. And then here we're just checking that it is on the curve which we've already defined. Then remember, we have the hashes, the SHA-256, and we have the other hash, which I forget the name of it, ripe MD160. All right, so these are the hashing operations, which, like I said, if you want to see how SHA-256 works, that's from scratch implementation, but it's basically just XOR and bit shifting, which is the similar concepts we have covered. So in essence, we have, let's say in this example, a secret key, which is the number given the passwords, the 20 passwords, for instance. You take that number times G. G is a point, gives you another point, right? And then you give this point here, and you calculate basically the address. And now this is your wallet address, okay? So whenever you have Bitcoin, your Bitcoin is going to be associated in the ledger with this address. So if you look, this is just a class public key, which has two functions. One is from point, which grabs the point, right? The public key obtained from the private key. And then basically it just calculates the address, all right? So let's just go to this class public key, which is up here. This one, public key. It takes a point, which is this point, and notice it's got X and Y, right? That's your public key in the elliptic curve that started from the G point. And then if you notice over here, we grab X, right? And we grab Y, the point, and we assign it to PKB. Do you guys see that? And what do we do to this PKB? What's that? So think about it, right? We have a point. The point has an X and a Y. And then that XY, if you notice, is just converted to bytes and added to this one or concatenated to this one. And this is just adding like some special parameters that it adds, and it becomes this variable PKB. And then what do we do to PKB? Hash it. Very good. We hash it twice, actually, right? So we hash it with SHA-256, and then we hash it with ripe MD160. Again, hashing comes in, and then this value, right, comes from this operation here in code. It gets assigned to PK bash. We add some kind of a version, and then that also is hashed twice to calculate a checksum. We add the checksum to the actual thing, and then we just encode it as we had discussed so that we get rid of things like 0 and O, right? We don't use that alphabet. And then that's it. So once you perform the operation, you get your secret key from your password. You get your public key from the secret key and the G. And then from the public key, you get the address basically. So here is the secret key that was calculated. Then this is the public key. If you notice, it's a tuple of X and Y. And then finally, we have that, which is the address, the wallet. Okay? Make sense? Any questions on any of that? All right, great. So we have a few minutes, so I really don't want to spend too much time on this part because I do think it's complex. I will just stress read through this. It's pretty long, but it's clear, actually. It's just more of how it works. So we talked about the mining, but this is actually, the mining would be you do this and you send it out. Do you see that, guys? And then someone else receives it in the network as a broadcast and decides if they're going to mine it, and they would use code like the one we discussed today, right? But now you want to think, okay, I need to create some kind of a transaction. The transactions are mainly going to be the simplest case, moving Bitcoin from one wallet to another wallet. That's it. And it's going to include the fee for the miner. So every time that you do a move of Bitcoin from one wallet to another, you have, so let's say you have, just to keep it simple, you have 10 Bitcoin, right? So you want to pay someone 5 Bitcoin. So you actually have 10 Bitcoin. You send it into two. You have to have, so you have one input, 10, which probably came from some other place. Where did it come from? Well, let's say that you just started in Coinbase or one of those. Okay. So you took cash and something called the faucet or the bank or whatever put 10 Bitcoin into your wallet. Do you see that? That wallet actually will be created by them also. So they would do all the processing. So now you have 10 Bitcoin. It's important to know that you keep track of where that came from. Everything can be traced from where it came from to where it is. Okay. But you have now 10 Bitcoin. You're going to pay someone 5 Bitcoin. So you're going to have one input, 10 Bitcoin, and two outputs. One output, obviously, the 5 Bitcoin that you're paying someone else. And the other 5 Bitcoin is actually something that you're sending to yourself to your own account. Do you see that? So that's the way that Bitcoin works, is like you have to do empty the 10 and just send it back to yourself. All right, so you have 10 to wallet A. You have two outputs, 5 to wallet B and 5 to wallet A, your own wallet, basically. That's it. All right, so that's the idea. However, there's going to be a little piece of money from that, from the Bitcoin that you're sending, that is going to be, let's say, to keep it simple, not 5, but let's say 0.10 of Bitcoin. And what is that? That is the fee that you're paying to the miner, to grab the transaction, to grab that transaction and do the thing that we just did with the mining code. Does that make sense? To add it in, so they're going to have a block, which is like the ledger, and they're going to put that transaction in there, and then they're going to start that whole hashing process to provide the integrity, right? To make sure that that transaction took place. Do you guys see that? So that's the incentive for the miners. They will get 0.10 Bitcoin, but by doing a lot of number crunching, as we saw in our example. So that's the idea. That's how it works. All right. So in a brief idea, I've given you that, so you can read through all of this and see here is an example, that shows, for instance, money that's being sent and the part that's going as the fee. So you can read through that, guys. And then here you have also, I want to also mention that there is a scripting language that was defined. And the scripting language looks something like this. So it's basically just opcode. So op dupe, op hash, the hash, op equal verify, op check sig. If you notice, these are just, so the miner, even though I didn't do this part in my mining code, the miners are also going to do this. So they're going to grab this transaction. Here is where I just like hand waved and called it data, right? I just called it data, but really that data is going to be something like a transaction. So opdupe just means duplicate, for instance. So it's going to duplicate whatever value is there, hash it, and compare it to this one. Do you see that? And then once you've compared it, they're going to do a verification at maybe the checksum, and then also the signature. Remember, it's going to have every transaction that you do. And that's kind of the one thing I want to conclude with today, because that actually is the elliptic curve signature. All right, so check sig here means check the signature. So it's going to check that elliptic curve signature. Okay. Does this make sense, guys? That there's basically a little programming language, right? That they have in Bitcoin. So whenever you do a transaction, you have to take everything, all your values, and put them in this type of little this programming language, which is basically like opcodes. And if you know anything about opcodes, it's like, whenever, like when you took ITS 450, and when you take ITS 450, you're going to see a little bit of assembly language, for instance. You'll see a little bit of that. And that's basically, if you know of a compiler, right? A compiler is you take something like C, C++, and you compile it to a whole bunch of commands, 0x30, 0x90, and those are called opcodes. And they're basically the commands that the processor interprets. So it's kind of like that, okay? It's a very low level language and also very small. Anyway, you have to learn how to create transactions based on this if you want to do this on your own. All right, and then, yeah, so that's the basic idea, crafting our transaction. You can read through it. This has the classes and everything. That's beyond the scope of what I wanted to cover, but I give this to you guys if you want to read through it so you can create the whole transaction through these classes, put it together. But this part I wanted to assume. So now imagine that you created the code, right? And it's basically 256 bytes or whatever of parameters, hashes, etc. So then now you're going to want to sign it. So in the past, we have used RSA to sign. And how did we sign? We would sign with our private key and it was verified with the public key. Remember that concept, which will be on the exam probably? Right? So that was the process. And this is similar, but it's just going to be with the elliptic curve approach. And so I have a function for that somewhere. I only have the sign, not the verify, but here it is. So this is you have the signature basically that you're going to create, which has these two values, R and S. And this is actually the sign with elliptic curves approach. So this is called your last topic of the course for the semester is the algorithm or the function, I should say, for the elliptic curve digital signature algorithm, also known as ECDSA. Okay, so that's it. So that this function here, which if you look, it takes in a message of bytes, right? It takes in the secret key that you've created in terms of the elliptic curve, right? That number at the very beginning. And then if you notice, it's going to take the order of the elliptic curve used in the Bitcoin. So what we define in the curve, notice, once again, what do? Take the message, hash it, right? You guys see that as being hash. And then from here, you start calculating a value, generate a new secret public key pair, right? Or use the ones that you already had. And then here is basically the math of it. Calculate the signature. That's it. So if you notice, inv is one of the things that was used in RSA, and then there's just some operations, mod n, right? If you notice. And then basically that's it. So yeah, so that is and then once you get the parameters R and S, these parameters here, you just instantiate an object called signature, and which is defined as just 2 ints, basically. Do you guys see that? So very, very quick, but I wanted to kind of show you this idea of the digital signature by using the elliptic curve algorithm instead. Okay, so I'm not going to really go beyond as we are out of time, but pretty interesting. Read through this one. And yeah, I hope you enjoyed. All right, guys. So let me end this.